Okay, in this video we are going to talk about doing integrals by trig substitution, which is kind of a neat way to do some integrals. It's basically u substitution, but it's a weird u substitution. So when are you going to use it? Well, you're going to use it when you see these sorts of things. So they're radicals. When you see them and it's not obvious what other method you should use. So maybe you try u substitution, but there's just some stuff left over and it doesn't work out. So this method will often work in those cases. So there's a couple of key steps. So the first one is that you're going to use the radical that you see to draw a right triangle. So maybe the radical could represent the hypotenuse, maybe it could represent one of the legs of the triangle, but we're going to use it to draw a right triangle. And then we're going to use the triangle to come up with things that we can make as substitutions. So you're going to want to make all of the substitutions. And this is actually one of the places where things go wrong for a lot of people because they forget to replace or to substitute for dx, which is actually one of the problems in general that people have with u substitutions. And then once you do that, you're just going to integrate. And so that part shouldn't be a big deal. And then once you've integrated, you've got to go back to the original variable, which is usually x. So we're going to sub back in. And the way that we sub back in is we look at the triangle that we made. Alright, so it's kind of an easy process to describe. Let's see if we can do it. So here's a problem. We have the integral of dx over x squared radical x squared minus 4. Okay, so there's a weird radical in there, so let's see what we can do. I'm going to use that to draw a right triangle. So there's my radical. Here's a triangle. So since it's radical x squared minus 4, I'm going to make that one of the legs, because if you think about the Pythagorean theorem, if it was the hypotenuse, there would be radical x squared plus 4, but it's not, so that must be one of the legs. If that's one of the legs, and again, think about the Pythagorean theorem, that means that x must be the hypotenuse, and 2 must be the missing leg that we don't know. And then I'm going to put in an angle, so I'm going to call it theta. And now we use the triangle to write, usually write two different trig ratios. And you don't want to use a ratio, typically, that involves the two parts that have x with them. So one ratio I'm going to use is tangent, because that only uses the radical part. So that'll have the radical x squared minus 4, and then over 2. And then another ratio that I can use that only has one x value in it is secant, or cosine, and then flip it over. But secant of theta is going to be x over 2. And then once I know that I'm going to look at the integrand, and I can see that I need to substitute something for x squared and something for the radical. And so since I right now have secant of theta equals x over 2, I'm just going to say x is 2 times secant. And I also need to substitute for dx, which again is the thing that people forget the most. So here I'm going to say dx is 2, and then the derivative of secant is secant theta, tan theta, d theta. Okay, so these are all the things that I get from the triangle. And now what I'm going to do is actually make my substitution. So I'm going to have the integral of, first thing I need to substitute for is dx. So dx in the box is 2 secant theta tan theta, and then d theta. Now I need to replace or substitute for x squared. So in the box you can see x is 2 secant theta, so I'm going to have the quantity 2 secant theta, and then squared. And then I need to substitute for the radical, and so I know tan of theta is the radical over 2, so I know that the radical is 2 tan of theta. Okay, so I've completely changed my integral. Now it's just in terms of theta. I can simplify this quite a bit. So equals, I get 1/4 because I got 2 in the numerator, and then 2 squared is 4 times 2, so 8 in the denominator, so 2 over 8 is 1/4. The integral of, I have a tangent and a tangent, so those are going to cancel. And then I have secant over secant squared, which is just secant of theta. Okay, so that's just by simplifying. So that's 1/4 the integral of 1 over secant is cosine, so cosine of theta d theta. I know the antiderivative of cosine is sine of theta, and then plus c. Now I'm going to go back to my triangle, and if you look at the triangle, you can see that in the triangle, the side opposite theta is radical x squared minus 4. The hypotenuse is x, so sine is going to be radical x squared minus 4 over x. And don't forget plus c. And there you go. So that's the antiderivative of 1 over x squared radical x squared minus 4. So the substitution definitely worked. Let's take a look at another one, which is going to be a little bit harder. So we have the integral of x cubed over radical 4 plus x squared dx. So again, there's kind of a strange radical in there. To me, that usually signifies I might want to try a trig substitution. So I'm going to draw a triangle. In this case, I have radical 4 plus x squared, so that's going to be the hypotenuse. So I can put the x and the 2 on either leg. I usually like to put the things with x opposite the angle, so I'm going to put x there, and then I'm going to put 2 there. And now what we want to do is come up with our ratios again. So I want a ratio that involves only x, like only one x, in either the numerator or the denominator. So tangent and secant look like good choices. So secant of theta is the radical thing over 2, and tangent of theta is just going to be opposite over adjacent, so x over 2. And then that means again that x is 2 tan of theta. And I can use this to find dx, which again is the single most forgotten thing when doing these. Okay, so that's all the stuff that I have, and now I'm just going to make a lot of substitutions. So the first thing that I want to substitute for is x, and I can use this. So I have x cubed, which means I have the quantity 2 tan of theta cubed. There's dx here, so never forget dx. That's going to be 2 secant squared of theta d theta. All over, now I have the radical. The radical is going to be 2 secant of theta from that. So 2 secant of theta. Okay, so that's all my substitutions. Now I'm going to simplify this. So I have 8, 2 cubed is 8 times 2 is 16, but over 2 is 8. So this is going to be 8, the integral of, I have a tan cubed and nothing's going to cancel with that, so I have tan cubed. And then I have a secant squared over secant, so I'm just left with secant of theta and d theta. Okay, so now this becomes, for some people, an annoying integral, right? It's powers of trig functions. So when I have to do this, I usually think about what am I going to let u equal? So if I let u equal just tangent of theta, then du would be secant squared of theta, and I don't have a secant squared, so that's probably not going to be a good choice. On the other hand, if I let u equal secant of theta, then du would be secant x or secant tan, and that I can actually make happen, right? If I save one power of tangent. But then I'll have a tangent squared, so I need a relationship I can work with there. But I know that 1 plus tangent squared is equal to secant squared, which means that tangent squared is just going to be secant squared minus 1. So that's what I think I'm going to do. I'm going to break this up. So it's going to be 8, the integral of, I'm going to take tan squared, I'm going to save one of the tangents, so then I have secant tan, and then d theta. I'm going to replace the tangent squared with secant squared minus 1. So this is all coming from the stuff on the right. And then I still have secant theta, tan theta, d theta. Now I guess I'm going to do u substitution just to make this look a little cleaner. I'm going to let u equal secant of theta, and then I know that du is going to be secant theta, tan theta, d theta. So it's actually working out to be a really nice integral. So it's 8, the integral of u squared minus 1, and then du. So this is, just reverse the power rule here, 1/3 u cubed minus u, and then plus c. And then remember that we made u equal secant of theta, so we can say it's 8 1/3 secant cubed theta minus secant theta, and then plus c. Okay, so I'm not done because I didn't get my answer in terms of x, but I did kind of integrate, so I'm kind of done. So I'm going to take the relevant information and start a new page here. Okay, so these are the things that I have. I need to replace secant of theta, so let me do that. So secant of theta I know is radical x squared plus 4 over 2. So it's going to be 8/3. I'm also distributing the 8, so I get 8/3 secant cubed. So secant is this, and then cubed, and then minus 8, and then secant of theta. And then plus c. There's a little bit of obvious stuff that I can simplify here, so I'm going to do that. So it's the 2 cubed in the denominator is 8, and the 8 over 8 cancel. And then 8 over 2 rather cancels, obviously, plus c. So you might choose to leave your answer like that, but it's possible that you actually would get a slightly different answer. So I'm going to factor this because there's a x squared plus 4 to the 1/2 in both of them. So if I factor that out, I get this. And then if I get a common denominator inside of there, I get this. And then if I take out the 1/3 and clean that up, I get this, which is maybe, if you use a calculator, this might be the answer that it gives you, so I just wanted to show that. Alright, so that's a couple of examples of integration by trig substitution. It's a really useful technique, especially when these weird radicals show up. I hope you found this helpful, and good luck.